Looking at problems 17 through 23 in Achieve section 3.9. The first one is asking us, it's a continuation of these problems where we're asked to find the equation of the tangent line. It gives me a log base 7 of the function 2z squared minus 113, and it's wanting the equation of the tangent line at z is equal to 9. Now, they put the equation y equals. When I think y equals, I automatically think in terms of x. Just remember, in order to get your answer correct, it needs to be y as a function of z, of course, since r is a function of z. Now, when I go into the problem, I can say, okay, this is the function that they gave me. Now I can say, well, I know that the derivative of every single logarithmic function in existence is 1 over what's inside the logarithm. And then the numerator is going to become times the derivative of what's inside, and that's just our 4z. Now also in the denominator, you'll see I had to put a natural log of 7. Please remember, that's only because this was the log base 7. That's the only difference in the derivative of a natural log and the derivative of the log of any other base, is you must put the natural log of whatever that base is in the denominator. So the derivative of any logarithmic function is 1 over what's inside the logarithm times the derivative of what's inside the logarithm goes in the numerator, and then multiply the denominator by the natural log of the base. Now I can say, all right, I need to find the equation of the tangent line when x is 9. So I plug 9 into this derivative, gave me a 36 in the numerator. In the denominator, it would have been 2 times 9 squared, that's 2 times 81 is 161. 161 minus 113 is 49. So I have 49 natural log of 7 in that denominator for my derivative evaluated at 9. Okay, now I take my point, which is easy to find out because I know the x value and the y value. You're just going to plug a 9 into this, which again is going to be 2 times 81, 161 minus 113 gives me a 49. So I have the log base 7 of 49. There's no reason to leave that in logarithmic form because we know the log base 7 of 49, that's literally just asking you, what power do I have to raise a 7 to get a 49? Well, 7 squared is 49. So I know that the log base 7 of 49 is 2. So my ordered pair is the point 9, 2. I know that this is the equation for my slope. So then I can say, well, all right, now I was thinking y in terms of x. So y minus y1 is equal to m times x minus x1. So y minus 2 is equal to our slope formula times x minus x1, x minus 9. You'd have been better off if you didn't do what I did and just go ahead and remember, well, your independent variable here, John, is z. So that should really be a z where the x is. I went ahead and solved for it. Now, unfortunately, I entered this answer in on Achieve and wrong. Well, the reason it's wrong is it just needs a z in the place of x. So please do remember that. Your expression needs to be a z in for the independent variable. Other than that, it's just like the problems preceding it. Number 18 gets away from those problems where we keep on finding the equation of the tangent line. And it asks us just to take the derivative, but it asks us to take the derivative with the process of logarithmic differentiation. So you'll see here, whenever we're doing this, you might say, well, I could take the derivative of that easy. That's an extremely basic product rule derivative problem. It could be. You could also just FOIL it out and take the derivative. But they're wanting you to take the derivative with logarithmic differentiation. So I say, okay, what's logarithmic differentiation? You just take the natural log of both sides, and then you use properties of logarithms to expand the right-hand side in this case. I know if I have a product inside of a logarithm, I can say it's the natural log of the first term plus the natural log of the second term. After you expand through properties of logarithms, then you take the derivative. I know that the derivative of the left-hand side, derivative of every single logarithmic function in existence, is 1 over what's inside the logarithm times the derivative of what's inside the logarithm. So we're taking the derivative with respect to x. So I have 1 over y times the derivative of y, which is dy dx. Now on the right-hand side, same thing. 1 over what's inside the logarithm times the derivative of what's inside, which again is just 1. 1 over x plus 1 times the derivative of the inside, still just 1. So I have these two terms on my right-hand side. In order to solve for dy dx, I would need to multiply by y on both sides. But you'll see that in the next step, I just multiplied by what y is equivalent to, because we want our answer in terms of x, not in terms of x and y. So I said dy dx is equal to all of that group times y, which is what I did right there with this and this substituted in the place of y. Final answer in terms of x. Please don't feel the need to simplify. That answer will be just fine. And you can see, in fact, that's what the answer that they want. It shows that you use logarithmic differentiation on it. Now, for my next one here, same idea. It just puts 3 terms in there. So I can say, well, all right, if I have 3 terms, then I take the natural log of both sides. And you'll see in my second step, I went ahead and used principles of logarithms to expand the natural log of the right-hand side. You would have 3 terms multiplied within one logarithm. Thus, you have 3 separate logarithmic equations being added together. Now we take the derivative, pretty straightforward. We get 1 over x plus 10 plus 1 over x plus 3 plus 1 over x plus 8. Since the derivative of each of those inside functions was simply 1. Then you can say, well, dy dx is going to equal what I have over here times y, but y is equal to this original, so we just bring that down. Fully factored final form of the answer. And again, could you distribute and simplify that out? Of course you could, but you're wasting your time if you do. They want the answer just like this right here. Now, up next, logarithmic differentiation is really more helpful in a problem like this. So first step is to take the natural log of both sides. That's what I did. Now, on that right-hand side, instead of writing the natural log of all of that group, just go ahead and expand it. I know that anytime I multiply like terms, those are going to be separate logarithms and they'll be added. Anytime I divide a term, it's going to be a separate logarithm that's subtracted. I also know that any power is going to come down in front of that individual logarithmic term. So when I fully expand the right-hand side, and you should be able to do this in one step, we'll get the natural log of x plus 3 times the natural log of x plus 3, and then minus, because it's in the denominator, 2 comes down in front, natural log of 2x minus 1. Now, I take the derivative of both sides. Left-hand side, as always, 1 over y dy dx. My right-hand side, first term, 1 over x, then I'll have plus 3 times the derivative of this group, which is just 1 over x plus 3. Then minus 2 times the derivative of this logarithm, which is going to be 1 over 2x minus 1, but then be careful, times the derivative of the inside, which is where that 2 in the numerator came from. I could have shown it out as 2 separate steps, 1 over 2x minus 1 times 2, but you might as well just go ahead and say that times 2 just means the numerator is going to be a 2. Derivative of what's inside always goes in the numerator. Now, when I simplify this, I can say, well, dy dx, I would have to multiply by y on both sides. I know y is just the original expression. The original expression will always be a factor in your answer when you use logarithmic differentiation. So dy dx is equal to the original equation times 1 over x plus 3 over x plus 3. Then I'll have minus 4 over 2x minus 1. Final answer there. A few more problems here. What if we move from problems where we could use logarithmic differentiations to 3 problems in which we must use logarithmic differentiation? So in that last problem, and in 18 and 19 as well, there's no need, I mean, other than it told us to use logarithmic differentiation, but I could have used quotient rule here, I could have used 3-term product rule here, and the 2-term product rule here, and no problem. So this just gave us another method to take the derivative, and I wanted to take the derivative this way because it told me to. But now in these problems, let's be very clear. You don't have a choice. So when it says, hey, use logarithmic differentiation to simplify this, why do you not have a choice? A lot of students would mistakenly look at this and think, oh, it's an exponential function. No, it's not. It's a variable base and a variable power. Then you think, well, maybe I just use the power rule on it. No, that only applies if you have like x to the second, x to the fifth. This is not either one of those. So I can say, well, all right, it's not an exponential, it's not a polynomial. There's no derivative rule to handle this directly. But it's very easy to handle if I just remember logarithmic differentiation tells us to take the natural log of both sides. When I do that, I know that any power on the term inside the logarithm can come down as a factor in front. So this simplifies to be the natural log of y is equal to 5x times the natural log of x. Then I can say, okay, now that's easy to work with because now it's just product rule on the right-hand side. Gorgeous. Derivative of the left, 1 over y dy dx. Derivative of the right, derivative of the first, 5 times the second, natural log of x, plus the first, 5x, times the derivative of the second, which is where I get my 1 over x. Then I can say, okay, now on that right-hand side, I can simplify it a bit. I can say clearly they both have a fact. Well, actually, I didn't factor out the 5. I just said 5x times 1 over x is going to be plus 5, and I'd get 5 natural log of x plus 5. I could have factored out the 5. I chose not to. So this is my right-hand side. Where did this come from? Because we had to multiply by y on both sides to solve for dy dx. Please remember, you want your answer in terms of x. So just say, well, y is equal to x to the 5x. That's the y term there, times the right-hand side simplified like that. And I could have moved that 5 out in front and called that the natural log of x plus 1. But this is the way I entered the answer in on Achieve, and Achieve liked it, as you can see right here. Now, on the next one, it's giving me a base x, and then it gives me an exponential function as its exponent, 3e to the 8x power. Whew, okay. So look what I did there. It's the same idea as the last one. We say, I don't have a rule to handle a variable base raised to a variable power. There's no rule that handles that. So since there's no rule that handles that, then logarithmic differentiation will help. And I can say, take the natural log of both sides. Now, this entire exponent on that x comes down as the term multiplying the logarithm. And I can say, okay, all of that comes down. I'll get 3e to the 8x times the natural log of the base, x. All right, now it's set up to where I can use the product rule again on the right-hand side. The left-hand side's super easy, just 1 over y dy dx. The right-hand side, derivative of the first, derivative of any exponential function is that exponential function times the derivative of its exponent. That's why I said, well, that 8 times 3 is going to give me 24 e to the 8x. All of that's derivative of the first times the second, natural log of x, plus the first, now times the derivative of the second, which is just our 1 over x. Now, when I simplified this expression, I knew I was going to have to multiply by y on both sides, which is just your original term here. And I could have wrote this out as multiplying that original term. I just looked at these two and I said, well, they both have a factor of 3e to the 8x. So I went ahead and brought that out front. You don't have to. So this came from the original. The y value had to be multiplied. This factored out of these two. When it factored out, the first term you're going to be left with is 8 natural log of x. And the second term, when you factor that out, all you have left is the 1 over x. So this is my fully factored final form of the fantastic answer. You probably could have not simplified it that much and still been fine with Achieve, but I like that answer there. The next one here, it's actually a bit anticlimactic from 22. 22 is the beautiful one. 23, you have x raised to the 3x squared. You take the natural log of both sides. That exponent comes down in front. multiplies. Now I use the product rule on the right-hand side. As always, when you take the derivative of the left, it's 1 over y dy dx. Derivative of the right, we're going to have 6x times the second plus 3x squared times the derivative of the second, which is where I get my 1 over x. Now, obviously, that 1 over x is going to multiply that 3x squared and give me 3x. That's why I got this 6x natural log of x plus 3x for that group. This is just when I had to multiply by y on both sides, and y is your original expression, which is always a factor in these answers. I could have also factored out a 3x, similar to how I factored this out of the last problem. I chose not to this time. And achieve does not have a preference whether you do or do not factor. Always, in general, a factored answer is always superior to a non-factored answer. It's just not absolutely required here. All right, guys, that'll do it for this section. Please let me know if you have any questions.